During this presentation, we have to concentrate on mechanics of a particle. For that, we should be familiar with certain fundamental things. Position vector and velocity. Let R be the position vector of a particle from the origin, and the velocity of the particle is V equal to dr by dt, which is equal to R single dot. Rate of change of position vector is our velocity, then dr by dt is given as R single dot. The linear momentum P of the particle is defined as the product of particle's mass and its velocity. We know the equation P equal to mv. Here V is replaced by dr by dt. Then dr by dt is replaced by R single dot. So P equal to m R single dot. Usually, the mechanics of a particle is outlined in Newton's second law of motion, stating that there are frames of reference in which the motion of the particle is described by a differential equation. According to Newton's second law, F is equal to dp by dt. Then replace P by means of mv. By considering mass of an object as a constant, we can write F is equal to m into dv by dt. Rate of change of velocity is our acceleration. Then replace acceleration by R double dot. We know that R single dot equal to dr by dt, which is equal to velocity. R double dot equal to d square R divided by dt square, which is equal to d by dt of dr by dt. This d by dt of dr by dt is our velocity. Rate of change of velocity is our acceleration. Therefore, the Newton's second law, F is equal to ma, is given by the second order differential equation am into d square R divided by dt square. Now we have to talk about consideration of linear momentum of a particle. As usual, according to Newton's second law of motion, F is equal to dp by dt. Suppose force acting on the particle is 0. If F is equal to 0, that is no force is acting on the particle, then dp by dt equal to 0. Then P is a constant. If you differentiate a constant, we can get 0 as a result. Now read out this statement. In the absence of any external force acting on a particle, the condition F is equal to 0 leads to the conclusion that dp by dt equal to 0, indicating that the linear momentum P remains unchanged. Next, we have to talk about angular momentum. We may study the angular momentum under two distinct circumstances. One is for a point object and another one is for extended object. For a point object, the value of L equal to R cross P. But for an extended object, the angular momentum L equal to I omega. We may arrive this relation from the equation L equal to R cross P. Then replace P by means of mv. We know the relation V equal to R omega, a relation connecting linear and angular velocity. This is our linear velocity, omega is our angular velocity. Then L equal to R cross m into, instead of this V, we have to substitute R omega, which is equal to m r square omega. mr square is our moment of inertia I. omega. We have had this result. By considering L equal to R cross B, we have arrived this result. For a point object, the angular momentum is L equal to R cross B. For an extended object, the angular momentum is L equal to I omega. You should know the difference between the point object and the extended object. In the case of point object, the object experiences acceleration while moving around a fixed point. But if you think about the extended object, it rotates around a fixed point. The example of point object is orbital motion of Earth around the Sun. The example of extended object is Earth's rotation on its own axis. Now we have to study the conservation of angular momentum. It is understood that torque is defined as the moment of the force. Torque N equal to R cross F. Now replace F by means of dP by dt. So N equal to R cross dP by dt. This is written as N equal to d by dt of R cross P. Here the equation is R cross d by dP by dt, but we are writing torque N is equal to d by dt of R cross P. How do we get this from N equal to R cross dP by dt? Now we will discuss. D by dt of R cross P, which is equal to dr by dt cross P plus R cross dP by dt. Here this dr by dt is our velocity. Then this P is our mv plus R cross dP by dt. See this V cross V is 0, parallel vectors. If these two vectors are parallel, then the theta value is 0. A cross B equal to AB sin theta, sin 0 is 0. So this term is vanished. Therefore we can write d by dt of R cross P equal to R cross dP by dt. So in this way, R cross dP by dt is replaced by d by dt of R cross P. We know the value of R cross P. R cross P is our angular momentum L. So torque equal to dl by dt. If torque value is 0, then dl by dt equal to 0, then L is equal to constant. When there is no torque acting on a particle, its angular momentum is conserved. Now we have to talk about a conservative force. A force is referred to as conservative when the total work done along a closed path is 0. See, A and B are two positions. This is path 1, this is path 2. The particle starts its journey from the point A and reaching B and then coming to the point A through this second path. The total work done in traveling the entire path is 0. So integral f dot dr equal to 0. It's a closed integral. A force acting on a particle is considered conservative if the particle's kinetic energy at the end of a closed path is identical to its kinetic energy at the beginning. If there is no change in the kinetic energy of the particles even after completion of one closed path, then the force acting on the particle is conservative. According to Stokes theorem, usually Stokes theorem transforms the line integral into surface integral. F dot dr present inside the integral is equal to curl of dot ds. Here the line integral is changed into surface integral. According to our definition, if the force is conservative, integral f dot dr equal to curl of dot ds equal to 0. Here ds not equal to 0, therefore curl of should be equal to 0. If curl of equal to 0, then f is equal to minus grade v. If curl of a vector equal to 0, then that vector should be negative gradient of a potential, a negative gradient of a scalar quantity. That is a general rule. Now we have to go for conservation of energy. For that, we should talk about work done in displacing a particle from one position to another. The work performed by an external force in the process of moving a particle from position 1 to position 2 is represented by the equation W12 equal to integral f dot dr, limit varying from 1 to 2. Usually replace f by means of dp by dt. Then p should be replaced by m into v. So W12 equal to integral m into dv by dt dot dr. We know that velocity v equal to dr by dt. Therefore, dr equal to v into dt. Now, instead of this dr, we have to put v into dt. Then cancel these two dt. We can get mv dv. M is a constant, integral v dv, limit varying from 1 to 2, which is equal to m v square by 2. This is the integral. V dv equal to v square by 2. M is a constant. Integral v dv equal to v square by 2. M is already present. Now we have to apply our limits. 1, 2. Take this m by 2 outside. v2 square minus v1 square. This is equal to 1 by 2 m v2 square minus 1 by 2 m v1 square. This is kinetic energy of the particle at the position 2. This is kinetic energy of the particle at the position 1. This is equal to T2 minus T1. So work done W12 equal to T2 minus T1. Here, if T2 is greater than T1, then W12 is a positive quantity. Under this condition, work is done by the force on the particle. As a result, the kinetic energy of the particle is increased. If T1 is greater than T2, W12 is negative. Under this condition, the work is done by the particle against the force, and as a result, the kinetic energy of the particle is decreased. Now, to get conservation of energy, we have to use the condition F is equal to minus grade V. You know the formula for work done, W12 equal to integral f dot dr. Then replace F by means of minus grade V. We know that grade V is our dV by dr. Grade V equal to dV by dr. Then this dr get cancelled. W12 equal to minus dV. If you integrate this, minus integral dV, limit varying from 1 to 2, equal to minus of V. Then apply the limit 1 and 2. This is equal to minus upper limit minus lower limit. If you use this negative sign, this is modified as V1 minus V2. Here W12 equal to V1 minus V2. The previous case we have arrived W12 equal to T2 minus T1. Then from these two equations you can write T2 minus T1 equal to V1 minus V2. Then T2 plus V2 equal to T1 plus V1 equal to constant. Here T plus V is our total energy. This is kinetic energy, this is potential energy. If the force acting on a particle is conserved, then the total energy of the particle is conserved. That's all about our conservation of energy.